All right, so we have this your second topic, which is the curvilinear motion. Okay, so this in this chapter you will learn about the representation of a particle. Okay, a particle moving in a curvilinear motion. Okay, so motion in a curve. Okay, this motion is described using three methods of analysis based on the XY axis, okay, NT axis, and the R theta axis. Okay, it is independent of chosen analysis method. Okay, and the velocity and acceleration in curvilinear motion always comply the two statement. Okay, shown in this figure here. Okay, as you can see. Okay, you have the figure there. Okay, one. Okay. One of it is velocity must always be tangent to the curvature and in the direction of motion. Okay, that is this first figure here. Okay, you see the first figure here where you have the curve. Okay, actually the the line there. Okay, that is your path of motion. Okay, so it's like you have a path of motion like that. Okay, that is your path of motion. Okay, and then you take any point on the path. Okay, let's say the first point is A. Okay, is A there. Okay, so you will see that the velocity, okay, the VA will be always tangent to the point A. Okay, so you take the point A and then you have to draw the tangent of it. That is the direction of your VA. Okay, at the velocity at the point A. Okay, the velocity of the particle at point A. Okay, and you cannot put it 90 degree or have any angle, okay, between this point A, okay, with the curve. Okay, it must be tangent. Okay, it must be tangent. So that will be your VA. And if you take the point at B, okay, let's say you trace and then take the point B there, okay, and then at point B you have the curve like that. Okay, so you have to draw, okay, tangent to the B. Okay, and the curve, okay, tangent to the curve. Okay, that is your VB. Okay, the velocity at point B. Okay, that is the VB. Okay, and then the second statement, the acceleration must always act inwards of the curvature. Okay, so the acceleration, okay, it could take any angle. Okay, your acceleration, it could take any angle, but you must know the acceleration must be in the inwards, okay, of the curvature. Okay, let's say at A, okay, you have the curve like that. Okay, so your A must be in inwards. Okay, di dalam. Okay, dia akan it must be moving inwards. Okay, of your point here. You have the point, and then your arrow must be inwards. Okay, of the curve. Okay, and then if at the point B also, okay, you have the curve like this. Okay, and then the curve is inwards of the curve. Okay, inwards of the curve. Okay, that is your acceleration. Always inwards. Okay, it doesn't follow. It doesn't necessarily follow the V there. Okay, but it must be inwards. Okay, inwards. Wait, you have friends. Okay. Okay, so let's say there are three cases. Okay, the acceleration and velocity, about the acceleration and the velocity. Okay, the first one, okay, let's say you have the path of motion, okay, like that. Okay, this one here, like that. Okay, and then you have, okay, for the V, okay, it will always be tangent, okay, tangent to the curve. Okay, so your V, then, okay, V tangent. Okay, so the first case, okay, you have the acceleration is at this direction here. Okay, so you have the V like that, and then your acceleration is at that direction. Okay, so if you have the case like this, okay, that means your particle is accelerating. Okay, so the velocity is increasing. Okay, it is increasing. Okay, the first case. Okay, and then let's say in the second figure here, okay, you have the curve like that, okay, and then V always tangent, okay, to the curve, okay, and then your acceleration is to the center of rotation, okay, your acceleration is at the center of rotation. So what happened to the particle, okay, is that at this time your velocity is constant. Okay, your velocity is constant. Okay, and at this time, actually, for the acceleration, you have two components. Okay, one is the A and then one is the AT. Okay, so the AT is the tangent acceleration. Okay, so the tangent acceleration, okay, at this time, okay, it is 0. Okay, when you have the A is only at the AN normal. okay, at the 90 degree from your V, okay. So this time, okay, there are no acceleration at the tangential axis, okay. So your V, okay, is constant, okay, at this time, okay. When you have curve, okay, you only have the AN acceleration, okay. And then in the third figure here, okay, you have the acceleration is it's like a opposite direction of your V. Okay, so your V is going there, but your A is in the opposite direction. So that means whenever you see something like this, your particle, okay, is decelerating. Okay, decelerating, and that means your velocity is decreasing. Okay, deceleration means velocity decreasing. Okay, your acceleration, okay, it is a negative. Okay, so these are the velocity and acceleration direction in a curvilinear motion. Okay, we go further. Okay, so this is the relationship between x's for the method of analysis. Okay, so under the curvilinear motion, you will learn there are three x's. Okay, the first one is the xy analysis. Okay, that's that one. Okay, you have this x. Okay, you have the y there. Okay, and then you have the zero reference there. Okay, 0 point reference. Okay, and xy. Okay, is taken from this reference. Okay, and then the second axis is the anti-axis. Okay, the anti-axis. Okay, you have the n. Okay, you have the curve there. Okay, and then the n will be always inwards of the curve. Okay, and then tangent. Okay, the tangent must be um, tangent to the curve. Okay, to the curve. Okay, and then you have the third, okay, what we call the third axis. Okay, that is the r theta analysis. Okay, r theta you will refer to the 0 reference. Okay, 0 point reference. Okay, here. Okay, but it will be on the particle. Okay, you see here the NT and the r theta. Okay, it will be on the particle. Okay, and then you have to build it. Okay, for NT you have to build it from the particle. Okay, for R you have to refer both. Okay, one is from the reference point. Okay, and also you have to refer to the point of the curvature. Okay, at the curvature. Okay, so for R, okay, you will have to draw, okay, from this point to the particle. Okay, that will be your R. Okay, that is the extension of the line will be your R. Okay, and then your theta will be the extension of theta. Okay, at that particle. Okay, so these are the difference between the axes. Okay, so you will learn these three. Okay, in the curvilinear motion. Okay, so we take a look first at the XY analysis here. Okay. Is there any of your friends want to join the? Okay. So we have this the first one XY analysis. Okay, so we use the XY axis to resolve the motion parameters. Okay, so it is typically used for the projectile motion. Okay, projectile like this. Okay, goes up and down. Okay, and you have this assertion of gravity. Okay, or what we call particles moving in a free flight. Okay, when you see the projectile free flight, free fall. Okay, that is XY analysis. Okay, XY analysis. Okay, so the projectile cases considered here have the following characteristic. Okay, the trajectory of projectile is assumed to be parabolic. Okay, you must know it must be parabolic um, shape. Okay, parabolic shape. Okay, the shape is parabolic. The equation are based on constant oscillation analysis. Okay, where your A is along the y-axis only. Okay, we consider the oscillation only on the y-axis. Okay, the motion parameters S, V, and A are resolved into X and Y components. Okay, later on you will see that your S, your V, and A can resolve into X, Y components. Before this, you only have the S in terms of T. Okay, but now, okay, you will have the SX, SY, and then you have the VX, VY, and then also AX and AY. Okay, in this case, your AX is considered zero. Okay, only AY will be the acceleration of the gravity. Okay, and then analysis typically involves 2 points. Okay, so you will have to refer to the reference, okay, because xy you will have to refer to its reference, okay, and then you have to refer to other particle, okay, other points, the movement of the particles, okay. So analysis usually it involves two point, okay. So we have this equation here, okay. This equation is actually comes from your, okay, rectilinear motion. Okay, so we take a look back at your rectilinear motion. Okay, the constant acceleration analysis. Okay, this one. Okay, case of a constant acceleration. Okay, where we have these three equation. Okay, the v is equals to u plus at. Okay, with v is the final velocity meter per second. Okay, u is the initial velocity. Okay, and then you have the a is the constant acceleration. Okay, in meter per second square, and t is the time. Okay, so this is the equation that you obtain from the slope of the what we call graph. Okay, if you still remember, okay, the v minus u divided by delta t is equals to a. Okay, this is the first equation. It comes from that. Okay, the slope of your graph. Okay, and then of vt. Okay, gravity. Okay, and then you have the second equation. Okay, v square equals to u square plus 2a times the s minus s naught. Okay, this equation comes from your equation of S. Okay, equation of S. Okay, where you have if you have a constant acceleration, okay, you will see that your S equation will become this power of two. Okay, power of two equation. Okay, and then also this third equation. Okay, it is equals to S minus S naught equals to ut plus 1 over 2 at square. This equation comes from the S equation. Okay, once you have integrate it, okay, where you have the t is the time taken from initial to final, your s is the final displacement, and s naught is the initial displacement, and a is actually the constant acceleration. Okay, and t okay, so what else? U v t. Yeah. So t is the time taken from initial to final. Okay. So this case of constant acceleration, okay, you can only use it, okay, in this type of question. Okay, this one here. Okay, because if you see it here, okay, this what we call the slope. Okay, uh, slope positive or negative. Okay, it will produce a constant acceleration, and then this, if you have a constant velocity, you will have the zero acceleration, but it is also constant. Okay, and this one also, okay, you will have a constant positive acceleration. Okay, so you can only use it when you have something like this. Okay, but you cannot use, okay, this equation. Okay, this equation here. Okay, if you have something like this, okay, the acceleration is not constant. Okay, this one, where this one, the acceleration is not constant. Okay, but you can use from the for the 8 to 14 second. Okay, and then you cannot use it here. Okay, from 1 to the 2 seconds here. Okay, because you see here, 1 to 2 seconds, your acceleration is not constant. Okay, so for this equation, okay, that's why I didn't highlight it for you for the rectilinear motion. Okay, because it will confuse you. Okay, a lot. Okay, so but then, okay, we use it for the curvilinear motion, okay, for the xy analysis, because, okay, because the acceleration here, okay, acceleration is constant. Okay, acceleration is constant for the gravity. Okay, for the gravity. Okay, so for the curvilinear motion xy analysis, okay, we will use the constant acceleration equation. Okay, the constant acceleration equation. Okay, so from the constant acceleration equation, okay, you have to put it in two, okay, axis. Okay, one is y, okay, the analysis along y axis, okay, and then okay you have the analysis along the x axis. Okay, so we start with the y analysis because this is the one that will have the constant acceleration, which is the gravity. Okay, you see here the ay is the gravity, it is constant. Okay, so this is constant. Okay, ay is constant, it is equal to g. Okay, -9. Okay, you must put the negative, okay, in your equation. Okay, later on, -9.81. Okay, meter per second square, it is constant. Okay, so we can use the equation. Okay, so for the first equation, okay, I call it the first equation. Uy equals to vy, sorry, vy is equals to uy plus ayt. Okay, so the Vy is the final velocity component in the y direction, and then Uy is the initial velocity component in the y direction, and you have the Ay, that is gravity, okay, downwards. Okay, because we assume, okay, you see here analysis along y-axis positive upwards. Okay, positive upwards. If it is downwards, that means it is negative. Okay, so that's why you have this Ay -9.8 1 okay, meter per second square. Okay, and then the t is the time taken from initial to final. Okay, initial means the starting point, and final is the point that we want to analyze. Okay, initial to final. Okay, and then you have the second equation, this one here. Okay, so it is equals to vy square. Okay, it is equals to the uy square. Okay, plus the 2ay times the difference of the head. Okay, sy minus the soy. Okay, that is the second equation. Okay, so this one you didn't have the terms of t. Okay, so if you your question didn't have any terms of t, in terms of t, okay, you can use the second equation. Okay, and then the third equation is this one. Okay, sy minus soy equals to the uyt, the initial velocity times the time taken from final initial. Okay, plus the 1 over 2 ayt squared. Okay, so this one, if you have if you have to find the t, okay, or you have to find the this one, okay, the height, okay, in terms of t. Okay, so the SY is the final displacement component in the Y direction, and your SOY is the initial displacement component in the Y direction. Okay, that is the analysis along Y axis. Okay, and then we take a look at the analysis along the X axis. Okay, remember to the right is positive and to the left is negative. Okay, so we have the main equation. Okay, the first equation for X is the Vx is always equals to the ux. Okay, so once you have the initial velocity, okay, at the x direction, okay, ux, okay, it will always be the same with the vx. Okay, and then the second equation, okay, is the sx minus sox is equals to uxt. Okay, it is the difference of x s, okay, is equals to the velocity, initial velocity times the time taken. Okay, the time taken. Okay, and you have the notes there. Okay, analysis in x and y axis are independent, okay, of each other but linked by t. Okay, it is only linked by t. Okay, so the t here, okay, the t here, it will link to this t here. This one, okay, it will be the same. Okay, this one will be the same. Okay, for the 2 points. Okay, for the 2 points that you analyze. Okay, and the other, okay, it will be not the same. Okay, you see here the oscillation, the ay, okay, they are no longer ay here. Okay, because we assume that the ax is equals to 0. The a, okay, the oscillation only happen on the y axis. Okay, the gravity. Okay, the gravity. So that's why we only analyze the projectile motion. Okay, projectile motion. Okay, and then for the vx ux, no relation with the vy or ui. Okay, unless it is the resultant. Okay, so u is equals to ux square plus uy square root. Okay, that is the only relation. Okay, and then yeah, okay, only the t is related, okay, between the xy, okay, xy between 2 points. Okay, Okay, next one we have the observation on projectile motion. Okay, so for this topic, for this subtopic XY axis, okay, analysis, okay, we only consider the projectile motion. Okay, how do we identify it? Okay, we identify it when it says the particle is moving in free fall, free flight. Okay, before free flight, and then you have the projectile motion. Okay, so those three keywords, okay, find for it, that is the XY analysis. Okay, it will involve the XY analysis. Okay, so observation on projectile motion. Okay, if you ever what we call lambung, throw something, okay, upwards, okay, actually you will see that the motion of the things that you throw, okay, through, okay, it will follow this path. Okay, you have something like a curve. Okay, a curve. Okay, it will makes it will goes upwards, okay, upwards, and there will be one time it will reach the maximum point, okay, and then it will fall down, okay, and it will, usually it will be forward, okay, if you throw it forward, okay, if you throw it upwards, okay, it will also make the same shape, but maybe the parabolic will be um, smaller, okay, smaller parabolic, but the shape of the movement, okay, it will be parabolic, okay, and then you have this height, okay, the certain height where you can see, okay, if you see here the maximum point will be the D there, okay, that is the maximum point for this projectile, okay, and then if you start from the A there, okay, you throw it from A, okay, so at the A there you will have the initial, what we call initial velocity U, okay, and then you have some angles when you throw it, okay, and when you calculate it, okay, you can resolve it into the U X U Y, okay, U X and U Y. Okay, so at A, okay, that if that is your starting point or the initial point, okay, it will become UX, UY, okay, and then once it's moving up, okay, it will pass the point B, okay, and point C, okay. So as you can see, okay, if it is moving up, okay, your V, B, Y, okay, it became shorter. Okay, you see here, okay, VAY, okay, it is that length, okay, and then when it reach VBY, shorter, okay, and VCY, shorter, okay, and then at the D, your V dy is 0, okay, that is the time when it will reach the maximum point and it will fall back down, okay, and as it moving down, okay, down and forward, okay, you will see that your VEY, okay, it will again the what we call momentum, okay, it will fall down, okay, the VY VY will add up, okay, little, okay, bigger little, okay, longer little, okay, at F here, okay, you see it is longer, and then at the VGY there, okay, you will see that it will be the same as, okay, let's say the G is the same level as the A, okay, you will see that this VGY is the same long or magnitude, okay, as the VAY, but okay, in the opposite direction. Okay, it will be in the opposite direction. Okay, and you check also for the B and F. Okay, you see here the length, okay, or the magnitude of VBY and VFY. Okay, they are at the same level. Okay, they will be the same magnitude. Okay, and then VCY and VEY also. Okay, at the same level, they will have this same magnitude of Y. Okay, VY. Okay, and then maximum point 0. Okay, and then if you observe at the x direction, okay, here the Vx, okay, the Vbx, the Vcx, Vdx, okay, and then going down, okay, Vex, Vfx, and Vgx, okay, you will see that the velocity are the same. Okay, for the x direction velocity, okay, for the components of the velocity in the x direction, it will be same, okay, along the path. Okay, it will be the same magnitude. Okay, it at each point of the path. Okay, so that is the observation on the projectile motion. Okay, in the y-axis. Okay, and you can see it here. Okay, um, VDY will reach 0, okay, VA more than VBY than the VCY, okay, until it reach the 0 there, okay, and then when it moving downwards, okay, you will see that VGY is more than VFY and the VEY, and then for the component of velocity, it is equal when it is the same level, okay, but in the opposite direction, okay, one is upwards, one is downwards, okay. VDY is 0 at the maximum height, okay, and then the only acceleration, okay, unless stated otherwise, okay, for projectile free fall or free flight, okay, is only the gravity, which is the 9.81 meter per second square, and must be vertically downwards, okay, vertically downwards. So that's negative, okay, negative, okay. And then we have the observation along the x-axis, okay, x-axis there, okay. We assume to the right is positive, okay. You will see all the ax will be 0, okay, and your vx is always constant throughout the flight, okay, always constant, okay. Yeah, okay, that is the theory about the xy analysis. Do you have any question? Any question?